Okay, so yeah. Okay, so today we're going to see probability and probabilities and distributions. This is just going to be one lecture, and then the last one will be on optimization, like continuous optimization. So this is coming back to the book that we are following throughout some of the lectures, this one here. And yeah, let's go in. So the idea of probabilities is to quantify uncertainty. And you can find uncertainty in the data itself, the way you collect the data in machine learning problem. When you're trying to perform predictions on the data, how to model the uncertainty that you have about your prediction, and the uncertainty in the model itself. So how certain are you about the parameters? Then probabilities and modeling distribution is going to be very helpful when we learn generative models. It's going to be helpful when we do state estimation with partial observability. So I gave an example of state estimation in the first lecture where we have a Kalman filter, and the idea there is to model the distribution on the state space using a Gaussian. Probability distributions are also going to be helpful in making decisions in stochastic environments. So there the idea is to, model what the state is in terms of a distribution and not simply according to a point, and then take also a stochastic model of how our action as a system influences the state. So there, having a notion of probability and probability models is going to be helpful. It's very loud. Okay. So what are we going to talk about today? We're going to introduce the basic blocks of how our probability is defined, what is statistics, and then we're going to talk about common distributions. So in common distributions, we're going to see the Gaussian distribution, the multivariate Gaussian distribution, and then we're going to talk about the binomial distribution, but before that, the Bernoulli distribution, and then the binomial distribution, and how they have the beta distribution as a conjugate prior. And we're going to kind of unify all of that into the exponential family of distributions. So if we take our example here of an autonomous system, the belief on the state space, so X might be for like a self-driving car, X might be where we are in the world, maybe our orientation in the world, and we might have a Gaussian distribution on the placements of the car in the environment, or equivalently on the placement and orientation or position orientation of these of the objects, moving objects in the environment, like the pedestrians, the bicycles, the cars, so on. If we use a Bayesian approach to machine learning, we might have the data likelihood expressed in this way, where we have a conditional based on the condition on the parameters here. And kind of classic thing that is used in machine learning and statistics is the score function, and this is also based on, the derivative of the data likelihood according to the parameters, or the log likelihood actually. So just to mention here what the score is, It's very helpful in statistics. It's the idea of what is the parameter that increases the likelihood of the data. So what is the change in parameter that increases the likelihood of the data? So you can consider like a single data point. So usually this is done considering a single data point. Okay. So, first question, what is a probability? So just kind of a high-level definition of probabilities. They generalize logic reasoning, meaning how events are correlated. It's a formal way to express something that we could name plausibilities. So how likely events are, and how we can reason about these different plausibilities using the rules of logic. So we represent the degree of plausibility of a certain event, how likely a certain event is to actually have occurred or be true or have occurred by a real positive number. Then we base these numbers, like the way to combine these numbers, on the rule of common sense. So if we have two likely events, then the combination of these two likely events actually are true or happen is based on some kind of rule of common sense. And then the reasoning must be consistent with consistency or non-contradiction, which means that different means can lead to the same result. Honesty, meaning that all the data that we have seen must be taken into account when we make a kind of probabilistic model of the data. Reproducibility, meaning that if the data is the same, we get the same result. Okay, so that brings us to the kind of classic divide between people who see probabilities and statistics in a Bayesian way and in a frequentist way. The key idea there is that the Bayesian way of seeing things is to use probabilities to define the degree of beliefs. And the frequentist approach is to consider the relative frequency between the events as probabilities. I mean, that's kind of like the very high-level way of seeing things. You can also see it in how decisions are made based on a data set. And in one case, you'd be more interested to kind of marginalize over the parameters of the model, and in the other case, in terms of, so in the Bayesian case, I think you're more interested in the likelihood of the data, and is that true? And in the frequentist case, in the likelihood of the parameters. So you marginalize over the other quantity. Okay, so that's just a basic idea. A lot could be said about this Bayesian frequentist view, and we're not going to talk about this today. Okay, so the first thing we are introducing is we're going to introduce kind of like the basic framework for probabilities. We're not going to go too in depth in terms of the formal definition of probabilities. Just we have kind of like a basic definition of what probabilities are, and I'm sure you all saw some version of that previously. So the key, so here we're just kind of restating things that you probably have seen before. The key components are one, the probability space, so specifying events and probabilities. Second, random variables, so that means we transfer these events and these probabilities into some numerical space. And third, a distribution over the random variable. So how probable are the numerical value of the random variable? Okay, so that gives us our definition for a probability space. It's a tuple of three things. So here we are defining the first component here. It's a tuple of three things where we have the sample space, which is omega, we call omega here. And we have A, which is the, or alpha capital maybe, is A, is called the event space, and P is called the probability. Okay. So let's see an example. We have an example of the coin toss, where we have the probability space is the following. We toss a coin 2 times, and H means that we land on a specific side of the coin, and T means that we land on the other side, so heads or tails. And this is the sample space, so it's the potential or possible outcomes that we might have if we toss the coin twice. Now, the event space is going to be a subset of the power set. And here I outline what the power set is, so as using an example. So if you have a set of 3 numbers, 1, 2, 3, the power set is the entire combination of what you can do with these 3 numbers. So you can do sets of 1s, so either the empty set or each of the elements independently, or combinations of 2, or combination of 3, which there's only one set, 1, 2, 3, the entire set. So the event space is whatever, like a subset of this power set, and here we have this subset here. And an event is an element of the event space, and it's associated with a probability, which is a number between 0 and 1, and the probability of the entire sample space must be 1. Okay, so now let's define a random variable. Yep. The power set, so it's defined, so for a set of 3 elements defined here. So if you have, so here you have a set of 3 elements, 1, 2, 3, and the power set is going to be the set of all the possible set that you can make of cardinality leading up to 3. So cardinality 1 is going to be 1, 2, 3. Then cardinality 2 is going to be 3 sets of pairs of one of these 3 elements, and then the entire set. Okay, so the random variable. So instead of working with probability space, where we have omega, R, and P, A and P, instead we work with states. And the key idea there is that we have a target space, and the target space is just like a numerical space. So in omega and the events, they are just kind of symbolic things that might happen. Random variable, or the target space has actually numerical values. So the idea is that we have a mapping called the random variable, which maps the sample space, omega, to the target space, where we are then just reasoning about numerical values. So let's come back to our example of tossing a coin. So here we have these the sample space of combinations of 2 toss. And we can define the following random variable. I mean, this is one example of a random variable that we could define on this sample space. So we have x of having 2 heads, we associate it with the value 2. X of 1 head, we associate it with the value 1 as the first toss. As the second toss, we also associate it with the value 1. And then finding no head, we associate it with 0. So what is going to be like what is the nice thing about defining like this a target space and a random variable? What can we then do with that? What kind of statistics are we going to be, like examples of statistics that we're going to be able to do now? Yeah? You said, so as the final toss, what the result would be? Mm-hmm. Like what kind of statistics can we do?
As example, what is the probability of the second toss based on the first toss? And again, here it is very irrelevant, but this is just an example to use the event itself.
Mm-hmm. Yeah. So we can kind of abstract like the order. The thing that we're going to be able to characterize, for example, is the average value of how many heads did we get, or we might get, and we can express that numerically. We can also compute the variance, the standard deviation. These things are going to be allowed thanks to defining a target space. Do you want to say something? No. Yes. Yeah, okay, so the target space here is 0, 1, 2. And the mapping is what's above. So what is the association between the events and some element of the target space? And then, yeah, so we have the event space and the target space that are finite. Then the probability is going to be a lookup table, basically directly associating elements of the sample space to the target space, to a probability. Okay, so let's take an example for further of a random variable. We consider the following game. We draw 2 coins from a bag with dollars and euros. And so it's not tails, heads anymore. Rather, we pick in a bag some coins where some are dollars, some are euros. So this is the sample space, so all the possible outcomes. And this is our target space, 0, 1, 2, same as before. And we define the following random variable, which is, well, exactly the same. So if we get, this is basically counting the number of dollars that we get when we pick in a bag, respectless of which one comes first. Then we define the probability of drawing a dollar 0.3, and we consider the probability of drawing a dollar or a euro independent. Yeah. Which is probably not, right? So if you have like a set of coin, like, well, no, it is independent in this case, but it's not independent. If you draw a dollar first, then the probability shrinks down for a small amount to have a dollar. But whatever, we kind of don't care about that. We assume we have an infinite number of coins in there. Okay, so The question is, what is the probability of x is equal to 2, meaning we draw $2 from the bag? The way we express that is by having probability of $1 times probability of $1. So it's 0.3 times 0.3, and this is going to be 0.09 as a resulting probability. For x is equal to 1, we calculate what is the probability of having the joint event and the union of the two events, and there we add the probabilities. So numerically, we have 0.3, and then the probability of getting a euro is the kind of inverse of the other, so 1 minus 0.3, and we have that 2 times, and so that's 0.42. And then x equal to 0, meaning we have 2 euros. It's kind of the same mirroring as $2, and this is 0.49, so it's even more likely. The idea is that, so picking up a dollar is much less likely as picking up a euro, so we get the following. Okay. So, distribution of a random variable. So if we consider the subset of target states, of the target space, of states, the pre-image of S under X is the following. It's all the events in the sample space for which the random variable is in the subset of states. That's the pre-image under S. The probability of the pre-image of S is defined as follows. So we have the probability of the random variable associated with the subset S is equal to the probability of the random variable attaining a value in the subset of states. It's the here it's equal to the probability of the pre-image of, so this is exactly the same, so it's saying that the events are in the subset of states, and so it's the probability of the events such that the random variable attains a certain value. This is called the distribution of the random variable x. So note that we have P of x of s is equal to P of x inverse of s. So the mapping from an event in S to the probability of an outcome in omega in the sample state. Okay, so if T being the target space is countably finite, then the random variable is set discrete. And otherwise, like for example, if T is the real line or T is the Euclidean space, it is said to be continuous. Okay, so discrete and continuous probabilities. The way to refer to distributions is different depending on the target space being continuous or discrete. That's what I just said. If it is discrete, then we talk about the probability mass function. And if T is continuous, so the target space is continuous, a more natural way to refer to it is to talk about the probability of the random variable attaining a value in a small interval. And it is more natural to actually find the cumulative distribution, where we are talking about the random variable attaining a value that is lower than a certain threshold. Okay, so let's take an example of distribution for the discrete case. We have 3 values that are in the target space, x equal to 1, x equal to 3, x equal to 7, and some probabilities associated with these values. And yeah, we can represent the distribution in this way. And the sum of the probabilities associated to each of the values that the random variable can take is equal to 1. And here we have the values of the random variable. Okay, so a final distinction here is that we can have univariate distribution, which is what we're talking about so far, but we can also have multivariate distribution, and that simply means that the target space is basically higher dimensional, and or it's like the collection actually of multiple random variables. Okay, so in the case of discrete probabilities, if we have a multivariate distribution, we can model the distribution using a lookup table. So basically a multidimensional array. And here we have 2 random variables. We have x and y. And we can model the distribution by the frequency associated with the event as a number in this 2-dimensional array. What you have to note with these arrays is that basically each column sums up to 1, and each row also sums up to 1. This is the law of probabilities that we defined before. And the target space is actually the product of the target spaces associated to each of the random variables. So these 2 random variables are associated to a single omega, a single outcome space. That's the key idea. And that's why these things have to sum to 1. Okay, and then we can define 3 things. We can define the joint probability, which basically in 2D would be like that. So it's what is the probability of the random variable the first one attaining a certain value, while the second one attains another value. So here xi and yj. And so here, this is the, no, actually, this is not, this is the frequency, but I don't think it's normalized. So it would be the number of time that this event happens, and so you divide by the total number of events to get the joint probability. We're going to see this in more detail in the next slide. So then we write compactly the joint probability as the union of both of these events, and then it's written x, y, like that, small. The second thing that we can do is define what is called a marginal probability. So it's the idea of what is the probability that the event x takes the value x, small x, in respective of y. And the third thing is the conditional probability, meaning what is the probability that the event y takes, capital Y, takes the value small y, given that x takes a certain, we fixate that the random variable x takes a certain value. Okay, so these are the 3 things. Let's look into more details using an example. Yeah? Yes, I think you're right. It's not row or columns, and then you have to normalize. But we're going to see this in this example. Okay, so we have the table where Rj and Ci is the sum with respect to the rows and columns. And so we consider these two random variables, and ij is the frequency. So it's not the, I thought it was the probability, it's actually the frequency, meaning that it's an unnormalized number. So yeah, so the Ci is going to be the sum with respect to the column, and then Rj is going to be the sum with respect to the row. And n is the total number, like the total so n is the total number of events, I think that's what I wrote here, or events. So I think these would be actually, this number would be the cardinality of A. And the sum, so the sum of all the cell values would be the cardinality of A. And each of the numbers in the cell corresponds to how many of the elements of A, for how many of the elements of A do we attain a certain numerical value in terms of the target value. And because we map it to two different target values, x and y, we will have this structure here. Okay, so n is the cardinality of A, and the marginal probability, meaning the probability that event x attains a certain value irrespective of y, is going to be summing up the frequencies in the column and dividing it by all the possible events that might happen. So all the events, the number of events, like for example in column, we are interested in x4, for instance. The sum of the frequencies in column x4 is going to be all the events for which x attains at x4. And then the probability of that happening is x4 divided, is Ci divided by n. Same thing with the row of y's here. So the probability that y attains a certain value is going to be Rj divided by the total number of events in A. Now, for the conditional probability, and that's maybe a little bit more tricky, the way we compute the probability of, let's consider y attaining y2, given that we fixate x to x4, let's say. Okay. This is going to be all, how many events do we attain the value x2? Do we attain for how many events do we attain the value y2 given that we fixate y4? And that's just a frequency number, it's not a probability. And the probability is going to be that we divide by the sum of all the events irrespective of y in which we attain the value x4. So what is the probability of attaining x4 at all? That would be, well, that's the other one. Nj divided by ry here. Okay, yeah, so that's a little bit more tricky. Or maybe you have a question or a comment here. that makes us understand this thing better? Yeah. Yes, so we have all the events in which, let's say xi, so x is equal to xi is all the columns, is all the events in this column. And then we divide the portion of those events in which we attain yi by that, which is, yeah. We only consider the events in which we attain x4, and then take what is the fraction of events in which we would attain the y value. And we do this reversely for x and y. Okay, so that's for marginal probabilities and conditional probabilities. So for continuous probabilities, we don't reason in terms of probability mass. So here, what we just saw with the table is really nice. It's a probability mass function. And we can count things and normalize things in this way. For the continuous case, we talk about the probability density function, which is a little bit more tricky to work with. The way we define it is that it's a function that is positive everywhere, and its integral sums to 1. In the discrete case, we are talking about the real sum. Here we're talking about integrating the function over the entire domain here, which is RD. So then the way we define a random variable in this case is that we have the probability density function defined, which is f, and the probability of a given event is going to be defined over a small interval and be equal to the integral of the density function over that small interval. So yeah, so a, b, and x here are outcome of the random variable. So the associated the association between the probability density function and that random variable is called the distribution of the random variable. And yeah, so if we like the probability, and that's key, and that's like the a little bit counterintuitive thing, the probability of attaining an exact value for a random variable is 0, right? We always talk about attaining some local neighborhood around a certain value, and then we can talk about a probability. If we are talking about attaining a certain value, so it's easy to understand. If you have, I mean, it's counterintuitive, but then if you take the example, if you have the interval, let's say, between 0 and 10, and you can attain all the values between 0 and 10. And you take a random value in the middle because of the properties of the real line that you can always dive in and dive in and dive in. It's infinitely stretchable somehow. The fact that you attain a particular point on that real line is basically impossible or improbable. So let's say that you attain exactly 1.0001 exactly by drawing on a random number from the real line between 0 and 10 is impossible. That's the idea. But if I take a little neighborhood, then it will have a probability associated to it. So then the thing that we define is the cumulative distribution function. And that's basically the integral of the density function in the here defined in the multivariate case, from infinity up to a certain value of the random variable. Okay, so let's compare discrete and continuous case or cases. So on the figure on the left side, we have a discrete distribution, and it associates a value to each of the three events that we have. And, or actually, we might have other events, but they don't have any. They're associated with zero probability. So we have three events that actually occur, and they are all associated with probability 1/3. And on the other side, we have the continuous case where we associate a probability density function with with kind of an infinite amount of possible outcome of the random variable. And you see that, I mean, the key kind of non-intuitive thing is that the probability density function can have a value that is higher than 1, and nevertheless integrate to 1, because here we have most of the density is 0, so the integral is going to be 1. So that's kind of like the key difference here. The probability mass has to sum up to 1. The probability density function has to integrate to 1, which is not the same thing. Okay, so by constraint, the density, which means that by constraint, the density mass function will have values always lower than 1. Okay, so in the discrete case, we talk about the probability mass function. In the continuous case, we talk about the density function. The interval probability is not defined for the discrete case, and for the continuous case, we talk about the probability, the cumulative distribution function, the CDF. Okay, so that's just for the main thing here, and we can move on to Bayes' theorem. So there are fundamentally only two rules to manipulate probabilities. The first one is the sum rule. In the discrete case, it means that the marginal probability, if we have a multivariate random variable, x, y, or two random variables, x, y, the sum rule says that the sum of the probabilities with respect to all possible outcomes leading to values in y, or outcomes of the random variable y, is going to be the marginal px. So we can express this with an integral in the continuous case. So the sum rule is also called the marginalization property. And then we have the product rule, which is the following, which is saying that the joint probability between x and y is equal to the conditional probability times the marginal probability. That's it. That's how we reason using logic. So if we look at the product rule, when we were looking at this table and we were trying to express what was the conditional probability, and you said, well, it's like you look at a column, and these are all the events in which x occur, And then you look at the subset of the events where y occurs, and then you just kind of divide the number of events associated with x. You divide like which are exactly these events where y and x occur, and you divide them by kind of all the events where x occurs. So this is kind of what the product rule expresses here. So if I have x and y, this would be the entire, this would be the cell. And I can divide it by the marginal, which is the sum of the column, and I would get the conditional. Okay, so we have the sum rule and the product rule, and of course, the most impactful result in the entire probability domain is the fact, it starts from the fact that we have a symmetry of the product rule. So if we have P of x and y, it is equal to P of y and x. And from there, it means that P of x condition on y times Py is equal to P of y condition on x times Px. And by just rearranging the terms, we get Bayes' theorem, which says that the prior, something we call the prior, P of x, times the likelihood, P of y given x, is equal to the posterior, where we have normalized by the evidence. So we give names to each of these four elements of Bayes' theorems, and these are very important for all of what I said in the beginning. When we're talking about machine learning, we are going to use Bayes' theorem a lot. When we're talking about state estimation, we're using Bayes' theorem a lot. And when we're talking about stochastic control, optimal control, we're going to use Bayes' theorem as well. And we're going to use these different terms. So what is the prior? That's especially important in machine learning. I would say, what is the posterior, which is important in everything, because that's usually what we're trying to estimate. So posterior means like, I think it's best seen in the case of state estimation. You're saying, so x is your state, and y is your observation. And your posterior is saying, what is my state distribution condition on the observations that I had, or that I have. And we can reverse the problem saying, how likely is it that I observe something given that I'm in a certain state multiplied by the prior? And that's going to be extremely helpful in state estimation. This is the heart of the Kalman filtering system and Bayesian. Kalman filter is just an instantiation of Bayes filter, which is just the application of Bayes' theorem. So again, I will instantiate that saying the posterior in state estimation is, if I'm in a self-driving car, I'm interested to know where I am according to the environment. And the likelihood is going to be basically a model that is able to project for a given position the observations that I would have given a map. That's going to be the likelihood. And then we can extract the posterior based on simply that kind of inversion of the probability, or that symmetry of the product rule. Okay, so expected value and mean. What's important to note is that the mean value and so on, the expected value, these are deterministic functions of the random variables. And the example the most important examples are the mean and the covariance. So the expected value, we can arrive at the mean by first considering the expected value of a function g, which is a mapping from the reals to the reals of a univariate random variable here that we call p, which is distributed according to some density function called distributed according to some density function called p, is the expected value of g. The expected value of g is defined as follows. So it's basically integrating the function g with respect to the probability density function. So how would you define the mean? Let's move on. Okay. So if the random variable is discrete, then we can use the following formula, which is much simpler, which is sum over the possible outcomes that the random variable takes. And if the random variable is multivariate, then we can express the expected value of g as simply the expected value of all the dimensions of x. Okay, so the mean, we can arrive at the mean, is the case where g is the identity. So a random variable takes in numerical values, and in the continuous case, we're going to express the mean by simply looking at how likely a certain event is, or how likely a certain state or associated to like a target state is, and we're going to sum that over. We'll sum the numerical value that the random variable takes, and multiply that by the probability of that event, and that's going to give us the mean. Okay. So what it means is that it's just simpler to define the mean through the definition of the expected value of a function, and that function being the identity gives us a clear definition of the mean here. Okay. Okay, so a few notes on the modes and the median and so on. So the average is kind of, at least in the continuous case, is kind of an intuitive notion, but there are multiple versions of this kind of intuitive notion of average. There's first the median. The median would be the value for which, in the one-dimensional case, half of the mass is on the left side and half of the mass is on the right side. So what is the value for which half of the probability, so half of the values are smaller and half of the values are larger? That's a median. The mode is the value in the probability mass function, in the discrete case, that occurs the most. That's just the mode. Medians can be generalized to continuous variables by considering the cumulative density function. And for continuous random variable, the mode is a peak of the probability density function. So there may be more than one mode. But first, consider, well, so this is the case actually in the mixture of Gaussians that we're considering here. So generally a mixture is defined by summing over two probability distributions. And the mean is a linear operator. So we can show that quite easily. So actually the expectation is a linear operator. So if we have f defined as the linear combination of g and h, where a and b are just scalars, then the expected value of f is going to be the expected value of g times a, because a is just a scalar, and remember that the expected value is just the sum or the integral, and plus b times the sum of the integral. That means that if we have a mixture of Gaussians that have two, where there are two modes, the mean is going to be the linear interpolation between the two. Oh, yeah, sorry. Yeah, there's a typo here. Okay. So these are two-dimensional Gaussians. We haven't talked about them yet. I'm going to introduce them soon. But, yeah. So covariance and variances. If we have two linear variables, then the covariance is simply the expected product of their deviation to the mean. So it writes like this, and then we can define the variance as being the square of, the expectation of the square of the variation to the mean. So it's the covariance of x with respect to itself. And the square root of the variance is called the standard deviation. And by linearity of the expectation, we have the following, that the covariance between x and y is going to be the expectation of the product of x and y minus the expectation of x times the expectation of y. And if x and y are multivariate, we have the same expression, but just here we get the transpose here. So, the variance of a multivariate random variable is the covariance of same thing, so covariance of x with itself, and it has the following form. Okay, I'm going a little bit fast because I think we're running out of time. So the sums and transformations of a random variable are the following. So there we said that the expectation is a linear operation. So if we have two random variables, then the expectation of the sum of two random variables is going to be the sum of the expectations, and which in this case is the mean. And yeah, for the variance, it's a little bit more complicated because we have to include the covariance between x and y. And if we have a linear transformation, that's important here. So linear transformation of a random variable is going to have is going to simply be or an affine transformation of of the random variable is going to be the affine transformation of the mean. But for the variance, it's going to be the following here, where sigma is the variance, the variance of x, and A is the linear transformation of the state of the random variable. And the offset, because it's an affine transform, the offset doesn't have any impact on the variance. You can imagine that. If you kind of like translate a distribution and you look at the variance, then the variance stays the same. Okay, so the covariance between two variables. Sorry. Yeah, same thing here. The translation has no effect on the covariance between the two variables, and it's only the. Whereas y here, I think, I don't know, there's some kind of typo here. Okay, so I have to look that up. Last thing is the statistical independence between variables. So we basically define that by saying that the joint probability is equal to the product of the marginalized probabilities. Statistical independence, you will often see IID, independent and identically distributed, which means that any subset of variable is independent and that all come from the same distribution. That's from the identically distributed. They all come from the same distribution. Independent means that any subset of variable is independent from the other one. So in machine learning, we consider a lot of the data being just IID. That's an assumption, but it's often too strong, especially in reinforcement learning. Equivalently, we can define independence in the following way, meaning that the conditional probability of x over y is just equal to the marginalized xy. Xy over x, given x is going to be x of x, that the variance of the sum of the random variable is equal to the sum of the variances, or that the covariance between x and y is actually 0. So conditional independence is a little bit different. Yeah. Okay. So I wanted to talk about distributions. So we're going to talk about 3 or 4 kinds of parametric distributions. The first one, of course, is the normal distributions. You've all heard about the Gaussian distribution or seen it in class and so on. The multivariate distribution is simply the higher dimensional case of the one-dimensional Gaussian distribution. What's interesting about it is that the marginalized distribution, according to if you have a two-dimensional multivariate Gaussian distribution, according to one or the other, is going to be a Gaussian distribution itself. But in general, many named probability distributions were discovered to model a given phenomena. And interesting properties from a machine learning viewpoint are going to be closure. If we use a specific type, it will give the same type back. So that's, for example, especially the case in Kalman filtering. We operate a certain transformation on Gaussian distribution. We include the evidence in a certain way, and what we get as output is a new Gaussian distribution. So this idea that by using Bayes' theorem and integrating new evidence, we get the same distribution out is a key property for using a certain parametric distribution, and especially kind of this notion that we're going to come to of conjugacy. Okay, so the idea that they are constant size, so more data, we keep the same number of parameters. For example, that's the case of neural networks, but if we use a Gaussian distribution to model a specific problem, the Gaussian distribution depends on the size of the multivariate Gaussian distribution, but has a certain number of parameters, and we can throw in more and more and more data. The model remains of the same size. And it's easy to parameterize. So a group of such distribution is the exponential family. That's what we're going towards at the end. And members of the exponential family are the Gaussian, the Bernoulli, the binomial, the beta, and we're going to see those. So the first one, of course, is the Gaussian distribution. You all know it. It's parameterized in one-dimensional case, parameterized by two numbers, the mean and the standard deviation or variance, and that's it. So here, the numbers correspond to the variance, so the square of the standard deviation. So the mean will shift the Gaussian left and right, and the sigma parameter is going to spread out the probability density function, or kind of concentrate around the mean. So in the general high-dimensional case, it has the following form, where we have the inverse of the covariance, which it's called the precision matrix. It appears here and kind of measures how we basically take inner product between So it operates like an inner product on the random variable, and the norm of the covariance appears here as a normalization factor. So a special case for the Gaussian distribution is the case where we have no mean and our covariance is the identity. So meaning that every dimension of the random variable is independent. Because the covariance between the different random variables is 0. So this is called a standard normal distribution, and we will see shortly why this special case is interesting. There is a closed form for marginal and conditional distributions, and it's easy to transform since parameterized by mean and standard deviation alone. Let's see the conditional and marginal. So the conditional of the Gaussian is writes in the following way. So here we have x of y given p of x given y, where the mean, so the mean value mu here is the mean of the conditional, and the covariance is the covariance of the conditional. Now, how can we recover those given the covariance of the marginal? So the mean and the covariance of the marginal. Okay, so the mean of the conditional is equal to the mean of the marginal, mu of x, plus the covariance of x, y, which is the joint, times the inverse of the covariance of the marginal, but with respect to y, times y minus the mean of the marginal. And we can kind of further express the covariance of the conditional in the following way. So it has kind of a similar structure. It's the covariance of the marginal with respect to x minus the joint times the inverse of the marginal with respect to y times the other joint. Okay, so the marginal, when we are given the joint, Yeah, that was the definition actually. Okay, so let's take an example. So we have a two-dimensional multivariate Gaussian, and we want to compute. So here we have two random variables. We have x1 and we have x2, and we want to fixate x2 to a certain value of -1, and our joint probability has the mean 0, 2, which is what we observe here. Like the central point of this Gaussian here is 0, 2. So you see that x2 is 2 and x1 is 0. And then it has a certain covariance which has to do with these ellipses. So if we fixate x2 to -1, sorry, we can compute the mean of the conditional using that formula here. Oopsie, here. Okay. So we have the mean of x, which we can read directly here. Sorry. Yeah, so here. Then we have the covariance xy, which we can read here. And then we have the inverse of yy, which is this one. So 1 divided by 5, because this is for the high-dimensional case here. But the inverse of a matrix of dimension 1 is just a reciprocal. So it's just 1 over 5. And that's 0.2 that we find here. And then we have y, which in our case is x2. And has the value -1, sorry. And then -2 is is 2 here. So it's the mean value of y. Okay, and so now we have our new mean, which is 0.6. Same thing, we can calculate what the covariance would be, or what the variance actually, it ends up being a one-dimensional Gaussian. So what we have is a multivariate Gaussian. We take the conditional distribution with respect to a particular value of one of the random variables, and what we obtain is a one-dimensional Gaussian using these formulas. So that's the nice thing about Gaussians, or one of the nice things, is that they have a closed form conditional distribution. Mixture of Gaussians. So we already saw mixture of Gaussians when we were looking at the two different modes, and I said, okay, so by linearity of the expectation, if we have a mixture of Gaussian, the mean will be will be between the two modes. So this is just like making that a theorem. So if we have a mixture of Gaussian, meaning we have a mixture coefficient which is alpha, and our probability distribution is P of x equal to alpha P1, where P1 is the first Gaussian distribution, plus 1 minus alpha P2, so we kind of linearly interpolate between P1 and P2. The mean would be the interpolation and it would be based actually on the mixture coefficient. So it's not exactly in between the two. It will depend on what is the mixture coefficient alpha. And for the variance, we have a similar expression. So we kind of linearly interpolate the variances of the two Gaussian distributions. But we have these kind of extra terms that have to do with the square of the mean and that term here. So the way we come to prove this for the mean, it's quite straightforward. We have our definition of the mean as taking the expectation of the identity function of the random variable, and we plug in, instead of p, we plug in our mixture. So this would be true for any type of mixture. And yeah, so that gives us that formula here. So this was straightforward. A little bit more complicated for the closed form formula for the variance. But basically, we start in the same way. We arrive quickly there by linearity of these integrals. Or was it so? Yeah, no. So what we did, so we have a sum, we decomposed the integral in two, and then what we were faced with was x2 p1 x. So what is the expected value of x squared? And we can express that in terms of the variance and the mean of the distribution in the following way. So because by definition the variance is equal to, of a random variable, univariate random variable is equal to the squared, or the expectation of the squared of the random variable minus the squared of the expectation of the variable, we can express that the expectation of the squared of a random variable is equal to the squared of the standard deviation plus the squared of the mean. So that was what we have here. There. And then we need a few other steps considering that function again in order to arrive to that result here. But basically, if we want to have the variance, then we say it is equal to minus this expression here. It's basically this expression minus this expression, and this would give us the variance of the mixture. Yeah. Okay. I think actually that holds for any distribution. Doesn't have to be a Gaussian. Mm. Okay, so how do we sample from multivariate Gaussian distributions? So if we have, let's first see how we sample from the zero mean identity case. It has dimension d, and we want to sample each of the dimensions and come up with a vector where all the dimensions are sampled ID from a zero mean unit variance Gaussian. So if we are equipped with a uniform or a sampling procedure which allows us to sample uniformly between 0 and 1, which is kind of like standard on a computer, you can do that. The following nonlinear transformation, so we sample two numbers between 0 and 1. This U and W, this nonlinear transformation called the Box-Müller transformation generates samples on the unit Gaussian, for the unit Gaussian of zero mean. So we simply, it's just basically using x and y, using u and w as polar coordinates. And then, so sine 2 pi is going to give us kind of like where we are on the circle, and then the other is kind of stretching, and taking the log allows us to have like an infinite kind of mapping like that. And this, you can show that this is actually sampling the unit Gaussian. Okay, so uniform sampling between 0 and 1, kind of polar type of coordinate transformation, and we do that d time, and we have a vector sample from the unit, from the zero mean unit variance and distribution. Now the question is, once we have samples from those, how do we transform them in such a way that they have a certain mean and a certain covariance? And we can actually perform a linear transformation of the data point, but we cannot do it in such a straightforward way. So let's see how that works. We're going to use the following properties that we saw, that basically, if we have an affine transformation of a random variable, it's going to lead to an affine transformation of the mean, and then that the variance is going to transform in the following way. Then, what we basically pose is that the mean that we are sampling from is 0, and the variance from which we are sampling is the identity. So this means that if we want to sample points from a covariance sigma m, we need to identify A times A transpose to sigma m. So if we are given sigma m as our target covariance, okay, so for the mean it's super easy, right? Because we are basically saying the mean of our distribution is simply going to be B. So there's nothing to do there. You give the mean to the distribution, you add it to the random variable, but you can see this easily. If you have a multivariate Gaussian centered at the mean, if you want to have the same with a different mean, you simply add the mean to all your points, translate them in space, and that's it, you're done. The problem is that if you want to kind of like stretch and change the variance of your data, or the covariance, the idea is that we associate A transpose to sigma m. So what operation, if we're given sigma m, would give us A? I want to sample from sigma m, and the way we're going to do it is by having a linear transformation, but with respect to A. And the relationship between sigma m and A is that sigma m is going to be equal to A times A transpose. So how do I get A from sigma m? Yeah. Yeah. And which one is it called? So this is the Cholesky decomposition. So we decompose the covariance using Cholesky decomposition. We get A, and we sample using that algorithm on the left side from the unit Gaussian, and then we linearly transform our data points using A, or affine, using A and mu. Okay, so already running out of time. So we have the Bernoulli distribution. which is the distribution of a single random variable that takes values 0 and 1. And it is governed by a single parameter mu that represents the probability of the event to attain 1. So in the case of tossing coins, like that would be what is the probability of hitting heads. And we have we define the probability in the following way, which is quite intuitive. The probability of x, so hitting heads, is going to be so x is the So x is either 0 or 1. So basically, this is I don't remember. This is a convoluted way of like defining something very simple. So basically, you have the probability of 0. You replace x by 0, and this would be 1, right? And then so that gives you the probability of hitting tails, and then probability of 1 would be that this is going to be simply mu, and this is going to be here. This is going to be 0. So this is going to be just mu. So either a mu or 1 minus mu, okay? So the expected value of the mean is going to be mu, and the variance is going to be mu times 1 minus mu. The binomial distribution, so this super simple distribution, it's the distribution that we've seen so far in these binary cases. The binomial distribution is generalizing that idea to the case where we have a discrete probability distribution of k number of successes in a sequence of n independent binary experiments. So it's generalizing the distribution to x is, being z. So you can also see it this way. So it's governed by two parameters. What is the success probability of a single trial, which we called mu before, and n, which is the number of trials. And then you can define it this way. So n is the number of trials, k is the number of successes, successful trials, and p is the probability of success, 1 minus p is the probability of failure, and then you have the expectation, and the variance is defined this way. The beta distribution, and we're going to see in 1 second why beta distribution is interesting. It's a distribution over a continuous interval between 0 and 1, and it has two parameters that govern the distribution, which are called the alpha and beta parameters. And the distribution is defined in this more complicated way. But what we find again is kind of this mu here, which is the probability of success. It's not, I don't think it's anymore like the probability of success, but it has like a similar kind of shape as the Bernoulli distribution. But now it's defined over a continuous interval. And depending on alpha or beta, it takes all these weird shapes. It's a nice distribution, parametric distribution if you want to define something over a fixed interval. But there are also distributions where there's like really a single mode kind of Gaussian equivalent shrink to the interval 0, 1. So it's just one of these parametric distribution for closed interval. Why is it interesting? Because of conjugacy. So if you recall Bayes' theorem, where you have, on the left side, you have the posterior, and on the right side, you have the likelihood, and they are linked together with respect to the prior. The conjugate prior is a prior if it is of the same type as the posterior, then it is called the conjugate prior of the likelihood. P of y given x. And the key idea, so the example that we would give is that the example of the beta and binomial conjugacy. So we just saw that the binomial distribution is if I have a binary event that has a probability of success, the binomial distribution is going to tell me or give me a distribution over how likely it is that I get a certain number of events being successful or being true. If I perform n successive trials, so how many of those, if I tell you I want k events to be true, what would be the probability of that happening? So it defines a parametric distribution for what is the likelihood of having 1, 2, 3, 4, 5 successful events over n events. So there's the beta distribution is the conjugate prior of the binomial distribution, meaning that if I use Bayes' theorem to update the posterior using the likelihood, my posterior is going to be beta. Okay, so if I have a binomial distribution, which is the probability of observing x heads in n coin flips, okay, we place a beta prior on the parameter mu, meaning mu is by probability of success for a single event. So observing heads, period, of a single event. Then we observe x is equal to h, where h is heads in n coin flip. And we can update the posterior in the following way, where we have a binomial model for the likelihood, and we have a beta for the prior. So we have h, n, alpha, and beta as parameters. Our update is going to look something like this. We can refactor it like that and observe that this is actually a beta distribution. That's the notion of being conjugate prior. It means that if I do a Bayesian update of my parameters, my parametric distribution, using some prior with a certain parametric form, I get the same parametric form as output for a given likelihood parameterization. And we will say that then that function, that parametric distribution for the prior is the conjugate prior of the likelihood that I used. So, to summarize, you have the likelihoods on the left side. In the middle, you have the conjugate priors. So the Bernoulli and the binomial, so you saw that the beta is kind of weird. It's difficult to wrap your head around the beta, why it's in this form. So this is the justification. So why we see it, it's because Bernoulli and binomial are very easy to understand. They have to do with a probability of success for binary events. And the binomial is like the sequential case, and the Bernoulli is just the one-time case. Both of them have a beta prior. So it means the conjugate prior is beta, and then the posterior will be beta. And the Gaussian, of course, is also Gaussian, and that's what's really nice about it, and that's what leads to the Kalman filtering system. You can make a Bayes theorem update to your Gaussian distribution using a Gaussian prior, and you will get a Gaussian as output. And for the multinomial distribution, which we didn't see there, the conjugate prior is the Dirichlet distribution, which is very famous as well. Not maybe famous because of itself, but rather because of its conjugate prior relationship to the multinomial distribution. And I put the link of the multinomial distribution, which is a very, which has also a very intuitive definition. It's kind of the generalization of the binomial distribution. Okay, so, and I will finish there. I don't know if I really have time, but the exponential family, all of these distributions are members of the exponential family, meaning that they can all be written in the following form. So they are basically, they can all be written as the exponential of the inner product between something called a vector of sufficient statistics, phi, and you can parameterize phi in all these different ways, and this will lead you to the Bernoulli, the binomial, the beta, and all that stuff. They all depend on like a different version of phi minus a as a parameter of theta here. So phi is the vector of sufficient statistic, a is the normalization, also called the log partition function. And the example of the Gaussian, you just parameterize phi in the following way, where you have x and x squared. Then the exponential writes this way, and you can kind of pose theta to be this, and you get the Gaussian distribution out. So, yeah. And you can, but the idea is that every member of the exponential family has a conjugate prior, which is very often inside the exponential family as well. Example is the Bernoulli distribution, which we saw. So that's the way to express the Bernoulli distribution as a member of the exponential family here. And yeah, you can rederive everything and you get the beta distribution. Oh, sorry. The canonical exponential family conjugate prior is the following here. And this, you can see that this is actually the beta distribution. Okay, so that's it for today. We have that probabilities are a way to formalize decision uncertainty. The probability space is a sound definition of probabilities. Practical way to use probabilities are random variable, which represent events by numbers. You can have continuous or discrete. We saw marginal probabilities and conditional probabilities for this kind of parametric distribution, especially the Gaussian. And there are two rules for computing with probabilities, the sum and product rules. And from that, we can extract Bayes' theorem and define what is the posterior, the likelihood, and the prior. And yeah, and so from that, we kind of saw how we can kind of unify all of the, or some of the parametric distribution as part of the exponential family and express their conjugate prior. Okay.